Assalamu alaikum wa rahmatullah, everybody. I am Al-Wardat from the University of Sharjah in the United Arab Emirates, and my colleagues Abdullah Hussein and Inas Abarob from the University of Al-Bayt in Jordan. We are going to talk about astrometry from Hipparcos to Gaia, parallax discrepancy. So in this talk, we are going to focus on the discrepancy between Hipparcos parallax measurements for binary and multiple stellar systems and Gaia parallax measurements for the same systems. And we are going to focus on the case of the binary star Hipparcos 45858 as an example of giving a new dynamical parallax and a solution to say which is the true parallax measurement. Is it that of Hipparcos or that of Gaia? So, as the Lord Kelvin stated, you understand something truly only when you can measure it precisely. And Confucius says, only excellent measurement is better than many medical measurements. So when we go back to Hipparcos mission, which was launched in 1989, and the mission ended in 1993 with more than 120,000 stars into filters. It released two catalogs, the Hipparcos catalog and the Tycho catalog. The Tycho catalog contains around 1 million stars. But Gaia mission, which was launched in 2013, is a mission which is going to observe millions of stars. So when we compare the two missions, the Gaia and the Hipparcos one, we can see that for Hipparcos the magnitude limit was 12, but for Gaia it could reach 21 magnitudes. The completeness, Hipparcos mission completed 7.3 to 9 magnitudes, while Gaia is going to complete until 20 magnitudes. And the number of stars, the number of objects is around 120,000 stars for Hipparcos, while it could reach 1 billion star for Gaia. And of course, there are other more modern techniques of observations in Gaia mission. So, why binary and multiple stellar systems? As we know that the analysis of stellar binary systems is the most reliable and accurate way of estimating stellar physical and geometrical parameters, especially stellar masses. It emphasizes the role of binary stars in examining some physical and stellar evolutionary theories. Also, even high-resolution observation techniques like speckle interferometry or adaptive optics are not sufficient to determine the physical parameters of the individual components of binary and multiple stellar systems. That's why we need a new technique or to calculate these stellar parameters. Nearby stellar populations are occupied mainly by dwarfs of F, G, K, and M spectral types, which with metallicities in the range between -1 up to +0.3. And more than 50% of these stars are members of binary and multiple stellar systems. And we may discover more number of binaries and multiple stellar systems among nearby stars. Also, the sources of stellar parameters. We have the direct measurements, what we call observations, which gives us magnitudes, M1, M2, M3 in some cases. I mean, the magnitude of the individual components, M1, M2, M3, and so on. The parallax, we can measure it. The positional measurements, rho and theta for the orbital solution, I mean, for binary stars. Polarimetry, but nothing else. What about the calculations? What can we calculate? We can calculate here the magnitude difference, the Keller indices, U minus B, B minus V, and so on, orbital parameters, depending on the laws and equations. But what about the rest of the fundamental parameters? These parameters should be estimated using some kind of computational techniques, and we are going to use here Al-Wardat's method for analyzing binary and multiple stellar systems. So the authors of this paper, comparison of Gaia and Hipparcos parallaxes of close visual binary stars and the impact on the determinations of their masses. In this work, the authors found that there are discrepancies for more than 55 stellar systems with discrepancy more than 5 milliarc seconds in the parallax measurements between Gaia DR2 at that time and Hipparcos 1 and Hipparcos 2. Of course, these 55 stellar systems should be analyzed to say what is the exact parallax for these systems. These systems were found among a sample of 1,700 stars. These stars, all of these stars have orbital solutions in the 6th catalog of orbits of binary stars. In this work, we can see that the comparison between Hipparcos 2. So we ignored here Hipparcos 1 as the former study showed that Van Loon was right in his reduction. So we are going to focus and use Van Loon parallax measurements, Hipparcos 2, and the Gaia. So we have Gaia DR2 and Gaia DR3. We can see that Gaia DR3 is more compatible with Hipparcos 2 than Gaia DR2. What about this system? As an example, we can see that for this system, the parallax is 23 from Hipparcos, 23.44. It is 14.9 from Gaia DR2, and it is 19.97 from Gaia DR3. So we need to analyze the system to find the actual case, to solve this case. So we use this method, Al-Wardat's method. Using the method, we can see that. And using the parallax from Hipparcos, the positions of the two components are more or less around the main sequence stars. It is the same when we use Gaia DR3. That means the method is not affected that much by the parallax discrepancy. But when we use Gaia DR2 parallax, both stars lie below the main sequence, away below the main sequence, which means that the solution is not true. The parallax is not true. So we are going here to adopt the parallax at the beginning, so the preliminary adoption, because we are going to give a new parallax, dynamical one, depending on the orbital solutions from the 6th catalog. So the estimated masses using Al-Wardat's method are 2.49 when we use Hipparcos 2 parallax measurements, these two red triangles. Far below the main sequence when we use Gaia DR2 parallax, away here, and 2.48, which is almost the same as when we use Hipparcos 2, here when we use Gaia DR3 parallax measurements, the green diamond. So we introduced a new dynamical parallax, but the dynamical masses, if we calculate the dynamical masses using Hipparcos, it gives us 2.01, while it gives us 3.25 when we use Gaia DR3. So there's a big difference between even the two solutions, which are almost close, while it's 7.83 when we use Gaia DR2. Absolutely strange number here. That means the parallax measurement is not true for which is given by DR2. Here are the final results for this system: the effective temperatures, the radius, the vertical G, luminosity, polarimetric, absolute magnitude, the masses here for the individual component, and the spectral types. And the age, we found that the age of this system is 1 giga-year for both components, with a new dynamical parallax 21.8. So we are introducing a new dynamical parallax. If you look here, it gives this solution, and this is the age of the two components. The method, the used method is Al-Wardat's method, which is described in the scheme, and it's going to be described in the paper later. Thank you.